Well, thanks everybody for joining us for our session today. Amongst the numerous sessions that are very interesting sessions going on concurrently. I'm Doug Schuster. I work at the NSF National Center for Atmospheric Research, and I serve as the interim director for the Computation and Information Systems Lab. And historically, I've been in a position where I've worked as a data manager, and also worked as leading kind of our data management efforts at NCAR. So first, I'd like to invite all the attendees. We have a URL up here for the document for this session that provides an overview of some of the goals of the session, a little bit of background on the session, and I'd really like you to join that document and add your name and affiliation for attendance and check-in. So we can reach out if we need to in the future regarding, if you're of interest, if you find some of the topics of interest that we discussed today. And with that, we'll just go ahead and get going. In terms of what we'd like to get out of this session, data preservation's a topic that's on a lot of people's minds these days, but as a data manager and data steward, it's really one of our fundamental missions is making sure data is preserved for the long term. So I've always thought of it in context of, disaster recovery is one component of data preservation. And that typically involves, having a geographically separated copy of your data set at a different location to deal with natural disasters. And in the current environment, we've seen that funding can be a challenge as well. So that's something that we've been dealing with. Anyway, so we'll go through a real world scenario, and we'll start off with Jennifer Schopp from UT Austin. Who works at the TAC Computing Center, and then I'll talk a little bit, and then Tom Cram will follow it up kind of with the details of how we worked all together on this project. So thank you.
Great. Thanks, Doug. Right. So Doug said we're going to talk about a real world example of something that we had been talking about kind of loosely and then became critical really, really quickly. I'm going to start off with some background on the Texas Advanced Computing Center and Leadership Class Computing Facility, talk about the idea that we identified a year ago at this meeting in Seattle, and then how, all plans only last until contact with the enemy. Well, plans shifted, and then how we moved 14 petabytes of data. So what is TAC? The Texas Advanced Computing Center is part of UT Austin. It's the largest NSF-funded National Computing Center.edu computing center in the U.S. It supports high-performance computing, supercomputing, AI, analytics, big data. We've got about 200 staff members. We're actually located about a 20-minute drive north of main campus in the research campus, the Pickle Research Campus. We work with all types of science, big science, small science. Something like 95% of the jobs are one node or less, but that's about 3% of the compute time that we do. We've worked with over 120,000 users in our 25-year history now, and we're currently at a point where we get a job submitted every 7.5 seconds year-round. So we support science from NSF, DOE, DOD, NIH, NOAA, NASA, USGS, fisheries, you name it. We also support large data sources. So the new machine we're building, and we are host to an NSF-funded major facility called the Leadership Class Computing Facility. This is a new 10x size supercomputer with an exabyte of storage on tape and 400 petabytes of live storage. But it's taken a more holistic view of how we view science support. The new machine, which is actually in the process of being built right now, as I was telling somebody, we just started staff tours up at the new data center, which is, again, another 15 minutes north of where the rest of TAC is located. We've installed the GPU nodes. Right now, there's about 75 racks of GPU nodes. Each of them weighs over 6,000 pounds. So that's the size of 2 Honda Civics. They are beasts. Each rack has got, over 215 megawatts of power. Okay. So our original data center had the power equivalent to 2 racks of we've got 28 GPU racks getting installed. These are almost all up and running at this point. We're doing the final debugging of them. The staff have been running on them for about 2 weeks. Our initial public use we're expecting next week. Probably should have said 2 weeks out because you never know how things go. But those are the GPU racks. We've also got CPU racks that are going to get installed later in the year, plus storage. A lot of the storage is already there and up and running. This is 30 terabytes of storage. It's called a ruler storage. That costs $20,000. All of our storage for Horizon is solid state. We've shifted from this in part for reliability. Or that was the plan. When we spec'd this out a couple of years ago, this made a lot of sense. With the rising costs of NVMe storage, we're probably going to have to do some disks as a middle layer just because of the financing. But we have one of the largest .edu solid state storage centers right now. We also have tape. The tape store is always called Ranch. All of the TAC machine names are different things of cowboys. So they get confusing because we've got Ranch, we've got Corral, we've got Frontera, we've got Lone Star, we've got Tejas. Ranch is a storage. It's currently going to be just more than an exabyte of tape. We actually just got a delivery of over 1,000 LTO 10 tapes in the last couple of weeks because we were down to under 100 tape medium in-house, which was a little scary. We update our tapes every 7 years. So we copy over all of the old storage to whatever the new storage is, which is always called branch, and go from there. People ask why, aren't you worried about deleting this for space? All of the data from the last 3 years is smaller. It's a fraction of the new space. So it's just easier for us to do this. But one of the things you need to think about with tapes is tapes go bad. One of my former positions was at the Woods Oceanographic, and they had actually videotapes from Alvin, the submersible, that 20 years ago they were worried they only probably had 1 run left on them. And what do you do with that? So that's a whole nother talk and question. But we update our tape storage every 7 years. It takes about 5 between speccing it out, purchasing it, getting it installed, and doing the copy over. This is the new facility. This is what it looks like underneath the floor, because these are both water cooled and liquid cooled both. The doors are massive themselves. This was in early May. This was storage racks. These are some of the CPU racks going in. They're huge. So this is a standard ladder. These things are 9.5 feet tall. Each of them weighs 6,000 pounds. If you open the door and the floor tile in front of you is down, they tilt. We now have snarky signs up that says don't do that because of gravity. There's a lot of space to fill. This is Nathaniel, who is pretty well known around the HPC circles. He's 6'2". So we have a lot more space in this facility. In part, we're north of where we are now for the power consumption. One of the ways we did this machine that's different than the way a lot of other people do big machines and big storage is we started with the thought of how do we support science? So we identified a set of characteristic science applications that crossed a number of science boundaries. And our acceptance criteria isn't some benchmark that we can game the system and match and meet. It's tenfold improvement on all of these science applications. Some of that's through better software engineering. Some of that's through bigger machines. Some of that's through smarter architecting the machine and making sure that the machines and the systems that we're setting up meet real science needs. There's a list of the projects. I'm not going to go through them. But we've worked with all of these. They had funding to work with us as part of the initial construction phase, and they continue on. And there are acceptance criteria. So as we go through to decide whether we'll accept the machines or not, are there errors? We're working not with made-up benchmarks, but with real science. And this has continued. We're looking at how we can keep supporting this kind of science going forward. We now have a science liaison. That's my new title as of a couple months ago. Another line on my CV. We're reaching out to large science, all science, across the board, saying, how can we help support your science? We have a simplified allocation process for large science. Half a petabyte of tape, 20, that should be actually 200 terabytes of active storage. Sorry, that's wrong. 5,000 SUs on Horizon, a couple VMs if you want it as a front end to your data. We have additional support for end-to-end workflow, so you can move to our systems if you need that help. I'll tell you right now, this is all free. This is all paid for by NSF. Even if we charged you at your standard rates, it's somewhere between 6 and 12 times cheaper than the cloud, just for the service supporting. And that doesn't count the ingest and express costs that clouds charge you, which we never do. We also do other services, like we help support end-to-end science, end-to-end data transfers for scientists. And you don't have to have an endpoint at TAC. If you're moving large data sets between two other sites and you're running into problems, we have a whole team that this is what they do. This is like candy for them. Every time I bring them one of these problems, this is what they want to do, is figure out how can we move this data better from end to end. And it's not changing how you are moving your data. In most cases, it's looking at the underlying infrastructure and debugging it, because networks rust. Failures happen. They don't snap back to how they should be. Somebody puts in a new router. Somebody doesn't, upgrade something sitting in a closet somewhere. Somebody adds a firewall rule. So we're the group that can help you, can ask for the support. You can reach out to me. If you're a smaller user, we also have other allocation processes, but we're also very happy to discuss this. And so for the last year or so, I've started reaching out to different science teams, even before we had this formalized, and said, hey, how can we help support you? We're already working with a number of large-scale scientists. I think everybody's heard of the Large Hadron Collider. We work with both ATLAS and CMS, IceCube Neutrino. I actually have about 15 of these hidden in this deck if you want to look at yourselves. I just pulled out a couple of the bigger ones more relevant to geoscience. I've been doing a lot of work with astronomy. We're helping design the next generation VLA data centers. They're going to be producing over 40 petabytes of data a month, and doing the model, their modeling and reconstruction of things. So that's a really kind of scary problem. That's about 12 years out. The data movement isn't as scary then, but the storage is still going to be pretty fierce. We just started talking to Vera Rubin. We're going to be one of their data archive centers. OOI has been a longtime user of Slack. Of TAC. I looked up in the last 2 years, they've transferred over 400 terabytes of data into TAC, just as part of their standard process. And of course, we've been working with NCAR Geo because of previous ties. I don't even remember. How did we even meet, Doug? Probably at an ESIP meeting when I was at NSF 18 years ago. We said, hey, how can we help support NCAR, right? What do we think might be an option here? So we started talking at ESIP last year in Seattle and said, hey, what would make sense? And he said, well, we'd like to have a better disaster recovery for backups, because what happens right now is we fill up a tape and it goes into tape storage. And then when somebody has time, they get driven down to the main data center in Colorado. I'm like, yeah, we could do that. We can come up with a better way. And maybe, figuring out how to provide a ramp for NCAR users when DirectIO is not quite big enough or not quite meeting their needs. How could they run on TAC systems? Like, yeah, let's talk about how that. And we had various conversations, and then December came. And the threat to the NCAR data centers happened. And so the conversations sped up. And I'll hand this off to Doug for the next part. Thank you.
And then, if you have any questions as we go through these slides, feel free to jump in and let us know. We'll have time for questions at the end as well.
I'm going to grab one of the mics in case people have questions.
Yep. And we'll ask you to use the mic if possible, because, we're supporting and a virtual audience as well. So I'm briefly going to start off and just provide a quick overview of what NCAR is for those who aren't familiar with it. So it's a federally funded research and development center that's sponsored by the National Science Foundation. It's not part of a government organization. It's an independent nonprofit organization, actually, that's a federally funded research and development center. And it's comprised of 8 different labs and programs that collectively cover a breadth of research topics in our system science, from the effect of the sun on the Earth's atmosphere to the role of the ocean in weather and climate prediction, as well as supporting and training the next generation of Earth system science. And we also, really work as a community connector, really serve the university community in providing computational resources for university researchers. So if you're an NSF-sponsored researcher, you can get an allocation on our compute systems, kind of like Jen mentioned with the TAC resources. And then also, as we go into this, if you see a data set that interests you and you're a U.S. university researcher, you can actually get an allocation in our compute resources to, bring your compute to the data, kind of similar to the cloud model that we hear a lot about that the agencies are providing. So one component of NCAR are the various facilities it has to support some of these research goals that I just discussed. One is the Mauna Loa Solar Observatory, which is located in Hawaii. It's actually located on property, I think, that's owned by NOAA. And this is a fixed platform that's used to observe and study solar phenomena. And that's been up there for a long time. Actually, high altitude research is what started NCAR back in the late 1950s and 1960s. And that was the focus of the organization. Then we also have our lower atmosphere observing facilities capabilities. So these are airborne and ground-based instruments used to study and observe atmospheric phenomena, kind of in the lower atmosphere where our weather happens that we see as humans mostly. There's actually a different session going on. There's a lot of people here from that group, but that group's been around for a long time, and they'll look at things like how does this type of cloud form, over Argentina, that type of thing that can be used to inform weather prediction in the long term. And then finally, we have the NCAR Wyoming Supercomputing Center. And this hosts high-performance computing co-located with community reference data sets used to generate Earth system science simulations, perform data analytics workflows, and study the areas that I've discussed already. So these are the 3 main facilities that NCAR hosts that are physical facilities. There are also others related to community software. So as NCAR has organically evolved over time, different repositories have evolved as well to support these various facilities with their data preservation and access needs. So you have the Mauna Loa Solar Observatory Data Services. You have the Earth Observing Lab Field Data Archive, which has been built to host the observations collected through these field campaigns that I mentioned. And then finally, you have the Geoscience Data Exchange, and Tom will get into quite a bit more detail on what that is. But that hosts high-performance computing co-located with community reference data sets. So really, that's bringing the compute to the data. So this hosts large model outputs, things like that, as well as a number of selected observations. And we're in the process of actually consolidating and bringing these repositories together under the GDEX umbrella, because it's really of value to bring all of these different types of data to bear together. So briefly, I'm just going to, characterize these 3 different repositories. The Mauna Loa Solar Observatory really carries heliophysics observational data sets collected through observing platforms hosted at the Mauna Loa Solar Observatory facility from 1980 to the present. The Earth Observing Lab Field Data Archive includes observational data sets collected through temporally and spatially constrained atmospheric research campaigns conducted by the National Science Foundation and other agencies since about 1967. And then finally, the Geosciences Data Exchange includes outputs from global and regional Earth system science simulation experiments produced both at NCAR and by university partners, as well as selected observational products. So we have a wide mix of data in these different repositories that we really need to preserve for the long term, especially the observations that cannot be reproduced over time. So that's kind of what the challenge was that was presented to us. It's always been there in terms of data preservation. that I've mentioned and data resiliency in terms of how do we deal with natural disasters. But I think we've taken for granted that the community feels it's valuable to resource these types of capabilities for repositories to preserve observations for the long term until recently. And then these different facilities include a wide range of data volumes. GDEX, that includes these large model outputs, is 15 petabytes. The field data archives around 500 terabytes with all the instruments that it hosts. And then finally, monoloads, about 60 terabytes. And this is really focused on the quality controlled and statistically reprocessed products. There's the whole bucket of raw data that comes off the instruments that's in the native format that can sometimes be in a proprietary binary format. That's in its own bucket outside of this right now. So that's a different challenge in itself. So what we'll discuss here, what we came up when events happened in last December, what we came up with is how do we deal with this in a nimble way as fast as possible? So we came up with this concept of a time capsule snapshot. So really the goal is for NCAR, a third party, to access the contents provided by a data repository and disaster recovery storage that's geographically separated from our organization, and then have the capability to reconstruct what's available from that repository into a production repository service. So something that's existing, take the data and republish it in something that's already running. Or NCAR, a third party, can instantiate the repositories as they previously existed with all the bells and whistles that they had. So that's the full suite of software applications, web services, et cetera. So that was kind of the immediate goal, and Tom will be talking about that. I think we're just, at the start of it, basically getting a snapshot out of the building of what things look like, but I don't think we've achieved the goals of reconstructing by a third party at this point. So that's something that's under discussion internally and in the community at this point. But medium to longer term, we'd like to, go to a concept or pilot that's more of a shared data curation and access that has longer term sustainability. And we want to base this more on science needs on top of data resiliency. So people care about data resiliency, but they also want to get value out of that data. And that's kind of the enticement for this concept. So the goal here is to provide additional data access pathways for a global user community, including a broader spectrum of data proximate compute options. So we work with partners, in Asia and Europe, Australia, really worldwide, but it's really challenging for them to access our data products, and they want to, do data proximate compute like we do here, at NCAR, like we do on the commercial cloud in the US. So it's, that's how we entice them to participate in this. It's useful, let's say, for the German Climate Computing Center to have access directly to a range of NCAR produced data sets on their infrastructure directly for their scientific use case. And that also provides us value because that provides us data durability and resilience by having copies of our data hosted on other places. So that, gets the ensure continued curation and access and in the event that our data services are disrupted. And as part of this, we've really only try to limit this to data sets with open licenses, because when you get into challenges with intellectual property rights, data ownership, that gets into a whole different ballgame. So we've tried to limit this as a starting point to data sets under open licenses. So with that, I'll hand it off to Tom, who can talk about the process for moving things. So go ahead, Mark.
Just a quick naive question based on very old knowledge of NCAR. Mm-hmm. That's not all of NCAR's data, is it?
No, that's not. So those are the ones that are hosted in community supported data services or repositories. There's PI data that sits all over the place. So,
and what happened to the research data archive? Is that
Geoscience Data Exchange is the research data archive?
Okay.
So Tom will get into that a little bit. So there's been a lot of changes and rebranding and consolidation going on behind the scenes. So some of this is,
but there's a lot of sort of individual PI collections, and wasn't there an effort to bring those into something cohesive as well?
So there's an effort to get those into GDEX, which Tom is going to discuss, as well as a Zenodo NCAR community. So that's what's been going on there.
Okay.
So there was a lot of researcher data. So this is a challenge where all of us face, where it's just sitting on their home directory or wherever their laptop. And the first process was to inventory what's there and make it discoverable where it sits. So at least we know this exists. And then the next part of that was to migrate it to hosted repository services.
So, but it hasn't really been the priority for this sort of resilience initiative.
No, we're focusing on the curated data collections for this.
Okay.
So we're trying to get people into those services with the understanding that it's the responsibility of the data curation groups to support data resiliency. And it's not that's one enticement for researchers getting their data in these repositories.
Okay, thanks. So I'm Tom Cram. I'm at NSF NCAR in Boulder too. And so I led the project to transfer all this data from NCAR to Tech. And so I'll just be talking about that and basically about the nuts and bolts of what went behind that. And so Jen and Doug already mentioned the challenge. We were confronted with this critical task early this year of transferring 14 petabytes of GDEX data from NCAR to Tech. And we needed to do this as quickly as possible, given time constraints. So I'll be talking about just everything that went into this. I'll talk a little bit about, a brief GDEX overview, what GDEX is, then get into network engineering infrastructure, and also the perf sonar test that we ran before we started the transfer. Then also our data packaging strategy, and then we use Globus Transfer to move the data. And so I'll get into the details of everything that went into that, including the Globus endpoint infrastructure workflow and transfer and then provide a summary of the statistics after the transfer was completed. Then I'll get into future work at the end. Okay, so about the Geoscience Data Exchange, GDEX, its origins go back to the early days of NCAR, 1965, back when NCAR researchers and university partner researchers needed data proximate compute access to reference data sets. So they were, even back in the early days of NCAR, we were bringing data to NCAR, bringing the data bringing the compute to the data, so scientists could perform the research, and that's still true to this day. It's evolved to what is known as GDEX now. Mark, you had mentioned the Research Data Archive. Prior to GDEX, it was known as the Research Data Archive, and last year we rebranded as GDEX. And now GDEX is the common. It serves as NCAR's data commons, which is a space for scientific discovery and collaboration. We host quite a few curated data sets. These include data sets produced by NCAR and university partners for the geoscience community. Then we also have the complementary or redundant data sets from community partners such as NOAA, NASA, ECMWF, JMA. Some good examples of these are the ECMWF ERA 5 reanalysis, JMA reanalysis products, also NOAA, National Weather Service forecast products. These are all used by NCAR and university researchers for their research. We adhere to FAIR principles, and then we have a large number of targeted data sets that are engineered for AI readiness, analysis ready, to support AI and machine learning workflows. And then the key strength of GDEX is that it's integrated with the NCAR's HPC compute services. So NCAR and university researchers have direct access to the data. So this reduces the time to science so that researchers are not having to download the data to a local endpoint and wrangling with the data to get into the format and in order to do their analysis. With GDEX, they have direct access to the data. They don't have to spend any time getting straight to the science. We have a growing repository of notebooks, which are reproducible workflows that are in curated reference Jupyter notebooks, so that researchers can then access these notebooks and use them in their research workflows as well. Finally, for users who do not have HPC access to the NCAR computing system, we do also provide HTTPS access to our data archive. And this is primarily through the NSF-funded Open Science Data Federation, which is a distributed system of data origin and cache servers, which allows users quick access to the data archive around the world. Just some key statistics about GDEX. There's over 1,600 data sets, curated data sets in the archive. Total volume is over 18 petabytes, and that's continually growing. And in fiscal year 2025, we served over 35,000 unique users. So that just gives you an idea of the scale of the user community that we serve. Okay, so I'll cut to the chase. This is the summary of the bulk transfer from NCAR to TAC. We started this in mid-February. I think it was around February 15th or 16th. We completed the transfer on May 7th, so that took 84 days to do the transfer. It was 13.9 petabytes, and using Globus, there were over 4,300 individual Globus transfer tasks that we submitted to do this. Average transfer rate per Globus transfer was 2.5 gigabits per second. That transfer rate is the effective transfer rate that Globus calculates for each transfer. That includes all the overhead, not only just to move the data, but also the end-to-end overhead. For example, at the TAC endpoint, there's the disk cache that eventually writes the data to tape. So this effective transfer rate also includes that overhead as well. So 2.5 gigabits per second, that roughly translates to, I believe, about 1 petabyte every 4 to 5 days. That was probably the optimal transfer rate that we saw with these transfers. Okay, so our data bundling strategy, we identified just under 1,500 GDEX data sets that we wanted to transfer to TAC. The requirement from TAC was that they wanted, since we're writing this to tape, because there's a limited number of file references on their system, the minimum size requirement for these data files written to TAC was 1 terabyte. And so what we did was we aggregated all the files within GDEX data sets into tar files. And we played around with the size. We tried as large as 10 terabytes per tar file. But the issue with that is that with larger tar files, it took longer to calculate checksums. When we decided, with the sweet spot that we hit on was about 3 terabytes per tar file. And so we aggregated all the data set files into these tar files. For larger data set collections in GDEX that were, like a lot of these were larger than 3 terabytes. In those cases, we chunked each data set into smaller chunks, into smaller 3 terabyte chunks. For the smaller data sets that were less than 3 terabytes, then we aggregated multiple data sets into a single tar file. And then we use the existing tool that we already use for our standard data disaster recovery backups. So we were able to take this utility and apply it to building these tar files and then making the transfer to TAC. On the right is just a description of what data sets we prioritize for transfers, or which ones we identified to be included in the transfer. And these were the data sets that had irreplaceable observational data. So we have a lot of historical observational data sets in the archive, and then also any curated data sets in GDEX that are from NSF, NCAR, and university partner projects. And then also there's quite a few other non-redundant community reference data sets as well. What we did not include in the transfer would be the complementary or redundant data copies that were produced by NOAA, NSEP, ECMWF, and JMA, because these data sets are already publicly available at these other organizations, so there's no need for us to transfer them to TAC. Okay, so right before we actually started the transfer, we held a meeting with NCAR, TAC, and the Globus team. This was on February 19th. And we had a discussion with the Globus team on how to optimize these transfers using Globus. Globus has a lot of experience with these use cases. This is something that they really enjoy working on, where they've worked with other organizations to help facilitate these large data transfers from one endpoint to another. So we met with them to get advice from them on how to optimize this. There was discussion regarding, the optimum number of tar files to include in a single transfer task. We realized it really didn't matter whether it was a single tar file or multiple, and we decided the easiest way to keep track of and log everything was just to have a single tar file for each transfer. The default configuration for users using Globus transfer, the default setting is users are allowed a maximum of 3 concurrent transfers at any one time using Globus. The Globus team were generous and they increased our concurrent transfer task limit to 10, so we could have 10 concurrent transfers running at any one single time. So that was a big factor in how we were able to move this data so quickly. There was discussion regarding the parallelism configuration on the NCAR and TAC Globus data transfer nodes. I don't think we really got too far into that because it really wasn't much of a factor. But then eventually, at the end of this meeting, we set a goal of 20 gigabits per second sustained transfer rate using 10 concurrent transfers. So we estimated at that time it would take 2 to 3 months to complete the full transfer of 14 petabytes. And then lastly, Globus strongly recommended that we run a series of perf sonar tests prior to submitting the transfers, and that would give us a good idea to identify any potential bottlenecks along the network path, and then to do some tuning if needed. And so that's what we did. We ran these tests on February 12th. On the NCAR side, at NWSC in Wyoming, we have a 100 gig perf sonar node. And the initial test only returned 12 gigabits per second. And we were kind of scratching our heads about this. And we realized that at that time, there was a severed link between Wyoming and Denver that was under repair. And so the network was taking an additional hop from Cheyenne to Boulder and then back to Denver. So this slowed things down quite a bit. That was repaired on February 13th. And so we scheduled another series of perf sonar tests. And the maximum throughput that we measured then was 59 gigabits per second. So it was much better. So we were happy about that. So this would be the maximum, under ideal conditions, this would be the maximum throughput that we could expect for the transfer. This slide is for the network engineering people in the crowd, if there's any. This just shows the trace route that the network took between Cheyenne and TAC. Basically, the takeaway from this is like we did not find any issues with the trace routes or anything with the network or with the Globus transfers. The main bottleneck that we ran into was just the limitations with the disk cache buffer on the TAC end in order to write the data to tape. So these are the two endpoints that we use for the Globus transfer on the NCAR side, or the source endpoints. We used a guest collection that's hosted on our Luster file system. We have at NCAR, we have 6 grid FTP data transfer nodes running Globus Connect server with a 100 gig switch. And on the TAC end, we were writing to a map collection. This was the Ranch tape archive. That's running a single data transfer node running GCS. And as I said, they have a large disk buffer there for staging incoming data. And so the sustained tape performance for writing data to tape at TAC is approximately 10 terabytes per hour. So that would translates to 240 terabytes per day. And so that would be the maximum possible performance that we would expected to see from this. And we actually did see that on a few days. We were able to achieve close to 240 terabytes a day. Regarding the workflow that we set up, my colleague, Waji, was responsible for building the tar files. And then what I did was I wrote a simple Python script, which uses the Globus Python SDK, which provides quite a few convenience Python functions for submitting Globus transfers and monitoring them, and then collecting the statistics from the transfers after they completed. So this is a way of automating the transfers as they went along. We had a cron job running checking every 10 minutes. It was checking for any Globus tasks that completed. And it was just making sure that we always had 10 concurrent transfer tasks running at any one time. And then it will also check our staging directory for new tar files that needed to be written. And if it needed to submit a new transfer task, then it would grab one of those new tar files and submit a transfer for that tar file. And then this is just a rough timeline of the project from start to finish. So like I mentioned before, in mid to late February, we did run into some bottleneck issues on the disk cache at TAC in late February. We noticed that it wasn't going as quickly as we expected it to. We were also competing with other users at TAC. So it's not only, we were a special use case where we're transferring a large amount of data to the disk cache, whereas the other TAC users are just normal users backing up their data to disk or to tape. TAC had discussions talked to the vendor, and the vendor did some tuning to improve the performance. And so after that, like early March, then things really kicked in, and we started to see the optimal transfer rates. Prior to that tuning by the vendor, our initial estimate to transfer all this data was 4 months, or roughly about 100 terabytes a day. But once they got that tuned, then things really picked up. By mid-March, we had already transferred 4 petabytes. So that was after a month of starting the transfers. And at that point, we started having weekly check-in meetings between NCAR and TAC just to check in and talk about any issues that came up during the week and just plan ahead as well. And then after then, things went pretty well. And then we completed the transfers on May 7th, 14 petabytes and over 4,300 tar files. So just a brief comment on some of the issues we ran into. I already mentioned the disk cache performance at TAC that was resolved in early March. And then also the competing resources with other TAC users. If there was more usage from other TAC users, we noticed it because then the Globus transfer rates would slow down. But then days when there wasn't any other competition with other users, then we saw the optimal transfer rates. Another issue we ran into is while the workflow that I had set up with the cron was made everything automatic, occasionally I would have to log back into the TAC endpoints on the Globus UI. And this was a manual process where I had to go to the Globus website, log into the TAC mapped collection on their end, and I had to re-authenticate as myself as a user because what happens at the TAC end is under my TAC account, there's a field in my TAC account that provided my Globus identity. And what TAC does is it maps that Globus identity to my local TAC username. So it could confirm that this is me making the transfers, and it can map it to the local user TAC. And this required occasional re-authentication on the Globus interface to keep that going. So there were days when the transfer stopped. I didn't know why. And I realized this is what I needed to do. So there was occasional manual intervention that was required. I mentioned checksums before. One caveat about these transfers is because we had to do this as quickly as possible. And I initially had, in Globus, the default setting is to verify the checksum on the transfer. So Globus can confirm that the data was transferred successfully without any corruption, and Globus will verify the checksum on both ends. But with tar files that are multiple terabytes in size, this adds a lot of overhead. And just last night, I just did a Google search on, my question was, how long does it take to calculate an MD5 checksum for a 3 terabyte file? And the answer I got back was anywhere between 8 to 28 hours to calculate the checksum. So this is like a considerable overhead that we couldn't deal with at the time. And so we had to turn this setting off. And so we made these transfers without verifying the checksum. This is something we'll come back to and figure out ways to verify the integrity after the fact. And then last point, occasional system outages and regular maintenance on both an NCAR and TAC. We were able to pause the Globus transfers when these happened, and we're able to deal with it no problem. Okay, so looking ahead, a lot of the DGX data sets are not static data sets. They're continually growing and updating. And so one of the things we need to account for is go back and look at the data sets we have transferred to TAC, and then look at the updates that have been applied to these data sets after the transfer, and then make sure this additional data is also backed up to TAC as well. The NCAR, Earth Observatory, Observing Laboratory, and HAO, or the Mauna Loa Solar Observatory data, also are working on backing up their data to TAC. I think HAO has already completed their backups to TAC, but EOL is still in process. And then I've been in communication with both of them on coordinating this. And then Doug mentioned this. We don't want you to just put this data on the tapes at TAC and just let it sit there without it being used by anyone else. We want this to make this available to other users, and we want to talk about how we can support user access to access this data and use it, and how users can make the best use of it. And then also, Doug also mentioned ways to back up GDX services. This includes our web portal code, database backups, metadata database, also additional source code supporting all of the GDX portal and data services. This is something we'll have to discuss more and think about the best way of going about this. This would allow anyone at another institution, if they wanted to spin up, a duplicate of the GDX web portal on their server, this would give them the capability of doing that. Okay, so lastly, I just want to thank everyone who was involved with this project, Jennifer, Heo, and Doug Southworth at TAC. They were really helpful and supportive for this work. My colleagues at NCAR, Sewaji was the one who was responsible for building the tar files and preparing them for transfer. And then Bob DeTore, Riley Conroy, Doug Schuster were also providing support as well. And also Globus couldn't be more appreciative of their help and support. Vaz and his team are really supportive and great with anything related to Globus. And so they're very helpful in helping us prepare for this project and supportive along the way.
So yeah, USGS actually, their new supercomputer has just been powered up at the NCAR Wyoming Supercomputing Center. So we're acting as a co-location facility in addition to supporting NCAR computing resources. And one goal of that project, that collaboration, is to bring to bear USGS data sets alongside NCAR data sets to support a variety of Earth system science use cases. So that's what was being described there. And in terms of the other question, let's see here. Will GDEX support COG and ZAR on public network? So yes, there's a talk tomorrow about user adoption of cloud optimized formats. I think it's at 8:30 in the morning. Is that right? So like we are actually supporting ZAR access on the public network. I don't know that we have any COG data sets at this point. So that's both internal and external. So our users are primarily getting data directly from POSIX, but then we have the HTTPS access. So that's what, that's how we're supporting access on the public network. But one challenge is user adoption. You put all these great tools out there, but most people really don't know how to use them unless you're kind of a tech wonk. So we're trying to get that in place to really show people the power of using some of these capabilities. So now it's open for audience discussion. So I threw up some questions here. Yeah, go ahead.
Yeah, quick question. My name is Hunter Bronium with the Kentucky Science and Technology Corporation. Okay. I just wanted to ask, what was your all's mindset? Oh, this is kind of an open question for you all. What was your all's mindset during this time of data policy and data standards, and how that was going to change? What did that look like, if it even changed at all? And being able to uphold the policies and standards you all have put in place for etc. of years. I was just curious about your mindset going into this, about what that looked like and how you all handled data policy and yeah. Does that make sense?
Yeah, I think so. I mean, I think from our perspective, our fundamental goal as a data curator is data preservation and access for the long term that outlives us. Like I put at the bottom of this slide, big picture, how do we get data sets to outlive humans and retain the human knowledge and insights from those who originally created and curated a data set? If our ship's going down, it's our role to make sure these artifacts are preserved for the long term and they're made usable for the long term. So, we pivoted to how do we do that? And what we just described is one little piece of that, just getting it off the ship. Yeah. But does it have value once it's off the ship? That's the point that we're getting to now. How do we deal with that?
Okay. So, and I will say in terms of data access policy, we transferred over data sets that were fully open. TAC can actually implement all sorts of fine-grained data access as needed. I mean, for example, we're working with the Rubin group, the big telescope, and they have really complicated access policies where people from certain countries have access at different times. And if you're a postdoc, you have access when you leave that country for a period of time. And we can implement all of that. But in this case, we were only looking at data sets that were fully open. Okay, Steve had the next question, and then I think you, and then you.
Hi, Steve Diggs, Scripps Institutional Oceanography. So should the worst occur, ENCO goes dark tomorrow, you have the backup on TAC. Outline the steps that you need to take to get those data sets back into the hands of the people that use it. In particular, are the digital object identifiers pointing in the right place? Is the metadata, right next to the data as it is on the original site? What are the discrete steps that you can think of right now that you'd have to take to go from archive to active repository?
Do you want to take that one, Tom? Right now, it's not ready for that, I would say. Yeah. The AWS bucket might be closer, but
yeah, we also did something similar to transfer data into AWS Glacier. It was a smaller subset of data sets, but it was like the highest priority. And those data packages included file manifests, metadata that went, that was sidecar, that acted as sidecars to the data. So that was a better, that was a more complete snapshot where users could come and grab one of these tar files and look at the file manifest, understand what was contained within there, and be able to use it. The TAC backups are not quite as complete. It's like we had to do this as quickly as possible, so we just took our existing utility for disaster recovery backup, and we just bundled everything into tar files and just moved it.
We were shoveling because we had been given a 3-month deadline before we thought lights were going to go out. And we've got a meeting set up later this week to talk about some of these longer term acts. In our ideal scenario, this is not how we would have done it. In our ideal scenario, we would have had time to architect things. We would have had time to do this a little bit with foresight, do a lot of extra work around it. But in January, we were afraid the NCAR Wyoming data center would be shut off in May. So we just started moving data. We are meeting later in the week to try to figure out how do we now that we've got the data there, what makes sense in terms of going forward. And maybe we recopy parts of it to make sure that we've done it more correctly. Now that we've got a little bit of time and space, we can do that.
I think to answer your question, though, Steve, we need to get the components that are missing as they are with databases, web services, etc. And then you'd hire somebody with knowledge and how to access all that information for a bridge of 6 months to work somewhere at a minimum to do this. The artifacts aren't there right now for somebody without knowledge to go in there and reconstruct this thing.
Okay, this is Hai Liang from Justice and Goddard. I have a question about when you do the transfer, you pick up is that 3 terabytes as a table? Right? I'm just wondering why do you decide to make them as a table at 3 terabytes in particular? Because like you said, it's checksum verification is very expensive, right? So, and also on top of that, have you ever think about because MD5, I'm not expert on that, but I'm doing some research saying inherently is sequential, so you cannot parallelize them. So there probably some way you can optimize them, you break them down into, because it's a table, right? So, or you maybe have many files inside, or maybe you can break them down to chunks, and then each chunk you can compute the checksum and do the checksum of the checksum. It could be probably faster. And I'm just wondering why you don't pick up that one. And last question, higher level, is during the transfer, do you guys do basically the data will be in a frozen state, or it can be keep updated? And if it's getting updated, how is that global set doing the work? Or
that's 4 questions. So let's start with the first one.
Sorry.
No, you're good. So I will say it was in a frozen state, period. We did not deal with having data updating on the fly. That was completely off the table. We were shoveling data out as fast as we could. Size of tarball is something that Tom did a bunch of experiments on.
Yeah, so we just wanted to do initially just do a snapshot at that time, and then deal with the updates later. That's what one of the next things we'll work on. Tarball size, yeah. I mean, I have to talk more to my colleague Wah about this, but we tried everything between 1 and 10 terabytes. Wah felt like 3 was the right number. Maybe it came down to it takes a long time to build these tar files too when they're this big. So I mean, in a single tar file, there's just millions of files, and so it takes a long time just to build these. And so maybe it's possible that 1 terabyte was pretty fast. We felt like we could put more in there and not compromise too much on time, and so we landed on 3.
Yeah.
So
we did do some experiments in the beginning with how many Globus tasks to run and what size tarballs and such. And so, the first petabyte took almost 2 weeks to transfer. It got down to about 4 days a petabyte. So we were constantly trying to find the sweet spot and adjusting it as workloads adjusted and other things adjusted. the 3-ish terabytes, just, we did do some experiments. So, sorry, Matt's got a question, and then Matt.
Hi, Matthew Biddle, NOAA's Integrated Ocean Observing System Office. Fantastic work. This is really cool. Not cool, but really a fantastic use case of how to go through this process. One of the things that I've been thinking about is GDEX was an established system with an established architecture, and you kind of had to work with what you were given at that time. Are you all planning on writing up like a lessons learned if you were to establish a new repository? These are the architecture decisions you would make in order to facilitate these type of transfers or ensure backups and things like that.
Yeah, we want to do a retrospective, I think, once things calm down a little politically and court wise. But yeah, that's definitely in I'd say one thing that was good is we had capabilities to do this disaster recovery backup on-prem, basically, where we build tar files and write data to tape, and then it's taken out and driven down to, from Cheyenne to Boulder. So we're able to reuse that software for this use case with a few tweaks, because it keeps track of inventories, what's where, what, all that stuff. It just was tweaked a little bit. So one lesson is, what can you reuse as much as possible? But I mean, there's other things. Like, it'd be great to have, not have to react, but be proactive and have information ready to go so that we can do this when we need to do this.
So I have kind of a more technical question about how you manage this. Like, we have a much smaller case, like we have a 5 petabyte Ceph cluster. And we find that whenever we do some massive system operation, like back up all of our data, we end up with IO contention that basically causes the system to not be that usable anymore. Did you, on either end of your systems, run into that? And how do you work around these gigantic system transfers without running into like IO becoming debilitating?
I don't think it was much of an issue on the NCAR end. When we started this, we had 4 Globus data transfer nodes. And then I asked our admin to add some more, and we bumped it up to 6 to accommodate us. If you're using Globus, like, I think it's, the more data transfer nodes, the better to accommodate the usage, because our data transfer nodes at NCAR support not only this use case, but all the other users. We provide data access via Globus to our users. And so and then NCAR scientists use Globus to share their data with their collaborators. So there's competing resources there. So you want to say anything about the TAC end?
Yeah, the TAC end, it was a little bit more complicated, and we did run into some contention. We worked with our systems team, and we were allowed to take half of the bandwidth for the disk cache. The TAC systems weren't architected to do this kind of massive data transfer. This was kind of, this is an edge case that, of course, we could support, but it wasn't. If we were going to do this day in and day out, we would architect things differently, because the bottleneck was, things would get tarred up, they get shipped over the network, they'd sit in the TAC data cache, and then we had to load it onto tape. So more tape robots would have helped, a larger disk cache would have helped, a faster disk cache would have helped. We didn't run into too many problems because we were watching it, and we had other warning systems set up to warn us when things were getting a little stretched. But we also have an amazing relationship with all of our vendors, because we're such a big purchaser user. We do a lot of prototyping for vendors in this space. So we have people we can call and say, hey, this is what we're trying to do. What would you recommend? So some of the tuning we did early on, with the vendor was in, that was late February, early March.
It's a community file system, so we didn't see anything. The big contention that happened there is when somebody's running a big Earth system model and they're doing IO, and that's when that thing gets thrashed.
I'll give you this for now.
We didn't see that.
Okay, and we're told there's a question online. One resilience challenge is is how to preserve traceability to archive data sets if the original archive quote goes away. use cases, we as researchers submit data sets to GDEX as part of the formal publication process. If GDEX goes away, how can future users of the publication get access to the data in the secondary repository? We're working on that right now. You know, as we've kind of said, we had to do this right away as fast as we could. So when I talk about data movement, I think of a lot of analogies with moving, you know, and you know, we were in a place where we had to throw all the books into boxes as fast as we could and get the box moved to a new place. Now we're in the process of, okay, let's unpack the books, let's catalog them properly, let's figure out how we can get better access to that. But we were in a situation that things just had to move, unfortunately. As I said, it's not how we had hoped to do this when we started talking a year ago, but you know, plans change when you meet the enemy.
And that's a big community effort. You know, I think how we've envisioned it is transferring ownership of the DOIs to the third-party repository, and then you can change the DOIs so they point to the data set landing pages where the data sets are hosted in the new space. That's the minimum thing, but you know, as we've discussed, there's a lot of human knowledge lost.
Yeah, so I guess so Mark Parsons, American Physical Union, is sort of picking up on that, because I think this is really where we're getting to the interesting meat of the conversation. I mean, this admirable effort you all did. Now, how do we make this like this? How do we make this sustainable? So I guess my first question is the plan to make this routine and operational? You know, so that this is an ongoing thing. So when something weird happens tomorrow, it's just a switch flip to tech.
That's our hope. That is the long-term goal.
And so now we have to figure out how to do that. Yeah. Okay.
Yeah, as long as they continue to be so generous, we'll take it. But
right, and then
we need community partners that are willing to do
yeah,
it.
and the question is, TAC any more sustainable than NCART? You know, that's the other question.
Yeah, we can make arguments about science funding, and you know, that's a good conversation. So I mean, the goal is to have a usable, functional backup of this data for users. So
Thanks, you guys. Really good. Nazla Radi from NOAA and CI. Just in general, the amount of meeting, coordination, back and forth, hostage negotiation it takes just to do one thing is almost impossible on a regular daily basis. And then when you put the pressure of time and political wins and everything else, it's really impressive. It's almost like a story that you're telling. Did you have an existing MOU with TAC, or did that? I mean, it takes a lot of your discussion with your leadership in order to do this. And so this is in the future, what would be your first, making these connections are the most important thing, I think, to begin this. So thank you for sharing your story.
yeah, that's a great point. And this is a story, and you know, we have other. I think this in part grew out of at the Seattle meeting. I told a story about some data rescue we had done with Arecibo, which was similar in they had started to reach out to figure out how to back up their data, but in their case, the instrument collapsed and almost destroyed their data center. It missed it by 15 meters, and so everything freaked out, and then of course they lost it. But this was in many ways a special circumstance. I mean, obviously the monetary exchange from NCART TAC to do this formalized process backup system that people could access as needed. And along with that, you know, have the TAC machines be certified in their code so that and our users could seamlessly go back and forth. When things started happening in December and January, I think leadership on both sides said, what can we do? What corners can we cut? How can we make this happen? And you know, it happened. It was unusual. If someone else came to me out of the blue and said, "Hey, I'm a random person and I have 15 petabytes of data, could you help me out?" That would be a much harder conversation. But part of the role of the leadership class computing facility is to support science writ large, especially MRECs and NSF-based science. So we took this as this was part of our mission.
Question.
So, and that's in part why I have now a simplified allocation scheme. If you need up to half a petabyte of tape, that's a couple emails and a conversation, and you do a 1-page description of your project. And we're set. If you need more than that, it's a more emails and another discussion, but it's possible because we see this need. I don't know how many discussions you had to have on your side, but at least on the tax side, it was, I am really blessed to be working for smart people who try to do the right things.
You just said go. I don't know. Let's do it.
Or Jordan?
Yeah, Jordan Reed with Quasi. So I agree with what others have said that this is fabulous to have this presented, documented, and all the lessons learned following up. I'm curious about the size of this relationship and how you feel about the distribution of other much smaller repositories on the landscape and the timeline that those partners would have for awareness to be more proactive, and also the kind of more bespoke architectures behind those other systems, the problems that those can create. So I was curious about your thoughts on that. I'm going to try to sneak in a second question, which is, we're talking about disaster recovery events that may be in a certain geographic region, and we're also talking about funding.
Like, this is a venue, like, as I reflect back, if I wasn't part of this community, I don't think a lot of this would have been possible. That might be how we originally met, either that or an HPC meeting, but this was hosted at IU one time, so that might have been the place where we actually connected. Earthcube. So being part of this community is a huge part of it. And I think all of the points you brought up are things that we need to discuss, and use cases that are part of the data resiliency cluster that's here, where they're talking about funding and disaster recovery. I haven't heard the ransom one come up, but do some of the solutions we have in place support that use case already? If it's geographically distributed in a different facility, could I recover if I have the ransomware thing, if we do it correctly? So, but working together, I think that's the key part, and then we've had a lot of, the globe is interested. We've had a lot of offers for support from Australia, from European partners, from Asia. So that's how you deal with some of the funding challenges as well, because things ebb and flow. Like, their funding could go down and we need to help them. So I see this as a mutual relationship over time.
So I was put on the spot because I'm with AGU, and AGU is leading a data resilience project, the Global Data Resilience Project. And the goal is, just as Doug said, is to build the community that backs each other up. So we've been using the term mutual aid network, which we're not exactly happy with, but you get the concept. And how do you put that into actual practice? And so we have a bunch of task groups that are working on trying to put this together into a plan, and it's easy to be a little cynical, another paper exercise. But I think also, as we just saw here, there's a realization that this is real, that we have to do something, that science cannot continue to be operating in the way that it has operated for the last 50 years, which is fundamentally brittle. And so we need to be thinking about how we're going to be doing our science data infrastructure going forward. And part of that is, as Doug said, it's the community. We have to be backing each other up. We have to be thinking collaboratively as well as competitively. We need to be thinking of new business models. We have a business model group that's looking at trying to do this. It has to be seen as a societal-wide endeavor, that we're not going to go away from government funding, but government funding can't be the single point of failure. Or an individual government can't be the single point of failure. So this is collaboration at all levels. It's collaboration across repositories. It's collaboration across governments. It's collaboration across different sectors of society. Civil society needs to be playing a role in here. Industry needs to be playing a role in here. And so it's time to actually start thinking about how we build a sustainable science infrastructure. So I encourage you all to get involved. Talk to me. We'll be talking about this more in the data resilience session Thursday afternoon, because we're definitely building on the great work that ESIP has done on the crisis scorecards. So, yeah.
I get to disagree with Mark in public, but which I never turned down. I'm actually not disagreeing with you, but I do have a point for you, Doug, and I'm gonna do exactly what Jordan did. I'm gonna slide in a comment and a question. This, I would swear, stuff is real, and Mark and I wrote a paper together. Stay ready so you don't have to get ready, and we're not staying ready. We're going from terrified to neutral. And I don't know why that is. And I think your point, because it's so energetic to stay in this space of where you're trying to diversify your data, well, that's great. I mean, but this is how organisms get stressed and then they either evolve or they die. And I think one of the things that Mark was alluding to is we got to evolve, but we got to evolve on very short timescales. So Doug and team, can we get together in short order and produce a get ready kit? Meaning you're a repository, your future is uncertain, especially if you're federally funded. What are your first steps to do? What is the get ready part? Have your inventories, we've talked about this a lot, have your inventories ready to go. Know what your DOIs are, who is managing those DOIs, physically where are the data, how fast can you move them, how frequently are they accessed, and who are your users? Most repositories don't know this because with the way we're funded, we don't have to. But I'm going to say that we need to move that timeline forward to produce that document, even if it's just a one pager, because most repositories freak out first. It's like doing a hackathon. Everybody starts from first principles and they build up thinking that their situation is unique, and really it's much more cookie cutter. Also, did you use the CDAC kind of data disaster as a model for how to move data? And for those of you who don't know, Columbia last year got a cease and desist, which is very, very rare. Even though the machines and the storage was actually owned by Columbia, they got an order from NASA to stop serving the data. And they had to move in this very similar timeline, 3 to 6 months. Their stuff was real. It ended up being such a disaster because now the data are in two places. They're at NASA and they're back at Harvard Dataverse. So I just wanted to hear your views on trying to produce a get ready kit in a month's time, because we don't have time. I can't say that enough. We don't have time. This administration is erratic, and the erratic is the worst part because we don't know when a head fake can turn real.
So I read the CDAC paper while we were doing this, so it was inspirational. But and then some of the lessons learned, I think that we can do that. I think we have to get a subset of teams together so we can, come to alignment on what that get ready kit looks like. Like I can publish what we've done and get that out there. So that's a starting point, and what we see the need to do is. But I think a big challenge is, I feel a sense of urgency because the fireball was thrown right at us. But people get complacent. Complacency is the biggest challenge, even within our organization. Just like we need to do this now, and so there's different levels of urgency even within an organization. And some are like, we're good. We're too important. That's not going to happen. It's like that's not the case. You're not doing heart surgery here.
Yeah. Well, so the question, that somebody asked is, how do you know the TAC is going to have any more chance of surviving than NCAR? And that's a really good one because, a year ago I was saying, hey, we got this major facilities award. So now TAC is, to HPC, what NCAR is to climate science. We're a line item in the budget. We will never go away. Yeah. We don't use that analogy much anymore, but part of how we are showing our worthiness and getting community support that you can't turn off TAC, quite frankly, is by getting data and getting end users. And if we are working with every MREFC, all of those science communities will complain if we get turned off. Look at what happened with the OOI data, right? They were supposed to cease and desist, pick up the buoys, bring them home. And there was enough of an outrage by the community because of the end users and the need for that data that got rescinded. It was a real panic for several weeks. There's a question of urgency, but there's also a question of exhaustion. So, and
so I wanted to pick up I wanted to pick up on what Steve was saying, because he's right. We're agreeing with each other, and that's one of the things the AGU is doing, trying to develop a crisis preparedness kit, and Doug's part of that. But I think these real world examples are what really help with that. So that's why I was asking about operationalizing this. You can't say you're done, and you're not, and I recognize that. And you're not even going to be done when you begin to answer that big picture question, because it has to be an ongoing thing. And the troublesome part is that this is yet an additional thing that repositories have to do, that are already strapped, that already don't have funding, that are already in a panic. But I think, just to be sort of reinforcing what Steve's saying, is your survival depends upon making survival operational. And so, yes, it's a new burden, but
yeah, and it was a lot of work, but you have to, I mean, is that part of your core purpose? Yep. No, I agree. Yep. And the crisis kind of prompted the opportunity, because otherwise they wouldn't have taken 15 petabytes of our data. You may have made us pay for it. Yeah. Okay.
So this issue that you describe of basically having all your eggs in one basket seems like part of the problem. Like whether it's located at NCAR or located at TAC or located anywhere, any one component of the system can go away. And we've been talking for years about distributed systems and networks as being the more powerful way of handling this. And yet I think repositories, largely because of funding mechanisms, are managed as independent institutions. But if we could inculcate kind of more of a network thought process and say, we're in this together, how do we make sure that the day-to-day operations are handled in a distributed system sort of fashion, such that there's never one copy of the data. There's never, your eggs are spread across multiple baskets, and there's not a dependency on a single one. I think for you guys, you are the largest data systems around in our community, at least. And the smaller repository systems have this problem in spades, because they are really isolated small groups, and much different from, say, a 15 petabyte NCAR archive. So I think that we should really think about how we can work as a network so that day-to-day operations are distributed.
That's a good point. And we're all building systems to do backups and disaster recovery and distribute. What are the goals of our CI? They're all the same. We're building 50 different ways to do the same thing. That's one area of low-hanging fruit that we have. And the human knowledge is what's unique. It's not the tech systems.
Yeah, so I'm Andrea Thomer. I'm with CSAR and at University of Arizona, and I teach digital preservation classes. So Mark just shouted out as an aside that libraries do this about the redundancy. And I've been thinking while we're having this conversation, in my digital preservation class, we teach the OAIS model. How many people are familiar with that? Oh, okay, great. And we teach locks, which is lots of copies keep stuff safe. And there are these models for distributed preservation that are to varying degrees implemented in libraries and in other systems. And like OAIS came out of NASA and not even out of the library universe. So part of what I'm wondering is, are there existing best practices we can kind of return to and ground ourselves in to forge a path forward? Like when I teach these classes, and in the past, I've been like, okay, what if there's a flood and your server goes out? And as I have gotten older and older, and my students stay younger and younger, they glaze over. They don't understand that the cloud isn't forever. They don't understand that the cloud is just somebody else's computer. And I'm wondering if there's I don't know that we need to reinvent things. I think there's existing technology from 1998 that we might need to recommit to. And go back from Web 3.0 a little bit. We need to, I don't know, 1.5, something around there might be good.
So I want to take your cloud comment, because we haven't really talked about the cloud. And a lot of people use the cloud as backup. And a lot of people saw how bad that was when certain government agencies had their front ends defunded. my team refers to using the cloud as burning your boats. Because once your data is in there, you don't have the money to get it out anymore, even if you had the time and space to put it somewhere else. So we do not recommend people back up to the cloud. I think there's a lot of these issues, and having some formalisms and some best practices would be helpful. I do think that the data sizes that most libraries deal with versus, so like the UT Austin library has a Texas data repository, and the largest file you can do, I think, is 10 gig right now. And you have to upload every file one at a time. So there's a different approach to 14 petabytes of data versus the data I needed for a publication.
I think the concepts can be reused. And we definitely we don't want to, in the spirit of open science, let's build upon the work that we have and capabilities that we have. We have a couple online questions, and when you're done, Stephen, we'll close it out.
Yeah, I just wanted to bring everybody down a notch, which is my function in life. But we have been given a gift, and the gift is we don't do fair unless we're scared. If you knew your data, no, I'm not talking about that's Martin is looking at me like, I'm not sure that's true. At a scale that it matters, I think we've been shown in the last 18 months. When the researchers have been coming to me in my institution, what do I do? And I give them the same talk that I gave 7 years before about verifying their data. Fair data almost never need rescuing, but we don't do fair unless we're scared. And we see it even with the most repositories that are under stress, that they go from, like a firefighter, right? 2 weeks of boredom and 5 minutes of abject terror. And we go back and forth to those two states. We've been given a gift. We know we have to be afraid. We need to stay afraid.
I'll do the online questions. And building on that, I was just in DC and talking to staffers, and they're just like, nothing happens here unless there's a catastrophe or a disaster, and then you can take the opportunity to get the money. So like right now, maybe there's a bit of an opportunity space as well. How much of the data archive rubric work that's been done on data value has been applied in all this work to create strong redundancy and resilience? And then shouldn't we be layering data value on here as a metric and looking for nonprofits backed by an endowment to take on the non-replaceable information? That's a different question. We could do a lot of research on that. We're not using it right now, but
NSF, when I was there, had the brilliant idea that the professional societies should be paying for the archives, not NSF. And I then, after I left NSF, spent a year at a professional society as a staff member. And they were like, we're supposed to do what now? Nobody told us that. There's no business model in that. We're not doing that. So I'm not saying that there aren't not-for-profits out there that wouldn't help support this. I mean, the Sloan Digital Sky Survey is a great example, but they're not funding that archive anymore either.
Foundations can
surge money. Yeah, foundations are primarily surge money
that can help us figure out the new business model, which will include an array of things like endowments and trusts and selling services, etc.
So there's a lot of models that we could look into. We just got the heads up that we need to break for lunch. I wanted to, can we go down?
Go back.
I wanted to say if anyone is interested in some of this, or if you're interested in how the leadership class computing facility might be able to support you, I'm actually giving a talk at the Woods Oceanographic on August 17th. There will be a virtual option. I don't have the link yet. It's at 1 Eastern on August 17th. And that's going to be open to the public. So reach out to me if you've got questions on that side of it. And we'd all like to thank you for coming in this great discussion. Thanks.